Alright, welcome to another Discus tutorial, episode 4. It's on structure creation. So today we're going to talk about structure generation from scratch, or how we may modify structures during the early stages in the main macro, in a whole macro set. Therefore, I brought along 3 nanoparticle examples. So we do that mainly with nanoparticles because the time for calculation is very short. And I have 3 examples here. The first one will be about an element. So elements are quite difficult to handle because they are consisting just of one atom type. So targeting and modifying, or for example doping, certain sites in an element is quite difficult, since you can't really get into the structure and find different arrangements and atom types really to start with your modifications. The second example I'll shortly introduce is LDHs, so layered double hydroxides. These are essentially host-guest systems. We will talk about how to layer them and mainly how to do your intercalation, so how you put guest molecules essentially within those different layer interspacings or kind of voids in your host structure. The third example will be essentially in core an aluminum oxide hydroxide. But the core is not as interesting, it's a layered material, but we mainly look there at the surface functionalization, how to work with surfaces and add molecules, atoms from outside on different surfaces of such a nanoparticle, where really surface functionalizations or stabilizers will become important in their scattering data. Last, it's not a really example, it's just an idea how to work with these structures, then what is required when we do a more detailed way of modeling. Alright, so the first example is boron, here shortly introduced. This element, the main building unit, is an icosahedron of boron, so at each corner of such an icosahedron are the boron atoms located, but in the structure of, for example, one polymorph, the beta boron system, we also have boron atoms which are not kind of connected to those icos or are not part of these icosahedra, and therefore it's quite difficult from the first glance to locate icosahedron and see what we may possibly do in terms of element replacement and controlled doping. So we will probably kind of disassemble this core beta boron structure and try to modify, for example, polar parts of the icosahedra and work a little bit with it, mainly with the connectivity menu. The second example we are going to introduce is the LDHs. So at first we will create a host structure. These are predefined sheets of such a metal oxalate, and we try to intercalate different guest molecules into the structure. And therefore it's important at first to create the structure of your guest and later on add the host to it, or the other way around. So in the beginning you need to have a model of each of those components. Then we throw them together with the domain menu, and then we can play around with it, do randomizations, add repulsive potentials, turn the different molecules, and so on. The third example is aluminum oxide hydroxide, or Boehmite, which can be seen here on the very left. It's a tower essentially of layered stacks of these aluminum oxide hydroxides. And we try now to work with the surface. We clean the surface up, and we will, especially here, have at least 2 surfaces we really want to try to decorate in the decoration menu of DISCUS. Therefore, we will differentiate between basal and lateral surfaces of the stack. So on the top and bottom, the basal surfaces, we have a very ordered way of hydrogen and hydrogen bonding, and we may put a few ligands to this very inert surface, whereas the lateral surfaces are very rough, and it's quite easy to have a strong interaction here with nest effects and other effects coming with the decoration, which can be seen here on the right with ethanol. So this is a non-covalent decoration with ethanol, and we can do something like that, a multi-shell assembly, but in our specific example we'll do a covalent complexation because they are easier to observe with standard X-ray methods. With that, we'll probably look into the macros now. Okay, then let's start with the macros. I've prepared 3 macros here, the boron one, the LH one, and the Boehmite, and we'll go through them in a chronological order. So we're going to start with the boron macro. So in the first step of this macro, we insert the boron structure, we expand the structure, and here we'll cut the block of boron atoms to a sizable rhombohedron. This should probably look like the upcoming JMOL window, which here wait returns until the next return and then continues the macro. So this is our first plot. So this is the beta boron structure in a rhombohedral shape, and we see that we just see a mess. So we were expecting icosahedra to modify, but we can't really see them. So now to organize this mess a little bit, we'll use the connectivity menu. This is the connectivity block. We add a connectivity between boron atoms of 1.73 angstrom to 1.99 angstrom. We create this connectivity and say that each boron which have in this range another boron with at least 5 neighbors to a maximum of 9 neighbors will survive, so will be replaced with carbon. All other borons will be replaced by hydrogen and discarded more or less. So if we do this kind of connectivity loop, we'll get to this picture. So now we do have the borons replaced by carbon, and the outer shell essentially, or the unconnected borons, which are now replaced by hydrogens, do not fulfill the connectivity condition, can be discarded. This is usually done for surface modifications in a general way and cleanup. But if you do that more times, so not just once, so if we repeat this step with this type of condition, so we replace the carbons again back to boron, which fulfill this condition, we'll do a loop 10 times over this block, then we'll find a few borons atoms will be left. And now we see icosahedron. So these are icosahedra were essentially hidden in the initial structure, and we have removed a lot of boron atoms. Now they are in the background, still H atoms, but we are not plotting them now. So having now this insight in the structure, we can do the modification we want to. So for example, we can work with the polar boron sites. So if we want to see the interconnections, we may certainly do that with another connectivity menu where we replace a few borons with this condition by helium. So we see now a few light atoms in there. If we zoom in here shortly, you'll see that the interconnecting atoms, boron atoms, are now at the polar sides replaced by helium. With that, we can do a lot of chemistry and exchange and modify our structure. In the next step, we'll just return the heliums back to boron, and we do that in a replacement in a more random fashion. So-called, I would call it pseudo-random fashion, because we are now replacing the atoms by their number. So this block is essentially saying that we replace now every 9th atom, so the modulus number of the atom needs to be less than 1, and at the same time the atom type M has to be 1, so it has to be a boron. And then this code line is executed, so we replace the borons by sulfur. This means that we now have replaced a certain number of borons by sulfur in kind of a rather random fashion. However, this method is reproducible, so you can now always replace every 9th atom, for example, and it will always be the same atom in this boron structure. So you see some icosahedra which are not changed, others have replaced atoms in them. Then what you can do, you can transfer all voids back into boron, and then you receive their initial structure, however with some atoms exchanged, so you can do doping with it at certain positions and so on. So you have quite a control even in elements with complicated structures such as boron is. Okay, that was it for the boron example. Now we may head to the LDH, and the LDH is a more complicated case. However, this one lives as it contains gas molecules. So we have a host structure with gas molecules which have to be defined in advance. So this is the part here on the top of this macro. So here several molecules, gas molecules are defined. So we have nitrates, then we apply a symmetry here, so we turn these nitrates and save them. So we have different nitrates. Here we have water, just an oxygen atoms, because the hydrogens are not that important in terms of X-ray scattering. So we have already defined the molecules which we would put in between layers of the LH. The next step is to create your host, and the host is built up by layers. So at first we have to define a layer. The layer is defined by the input structure. So the input structure is cut with within a certain thickness. So you go into surface menu and set boundaries and cut out a section of the initial structure, and you can save that as a layer. So in this case, a second layer is also saved. It's a rotation again, symmetry menu by 180 degrees, which essentially gives access to stacking faults. So when we run this macro to the first plot, which is this one, then we see exactly one layer of the LH structure. So this is the top one, and next to it, intercalation position in the gallery. So these are the positions we'll later replace with the guest molecules. Both layers together are essentially one layer and have to be stacked in the next step. This is done in the stacking menu. So here we load both layers, the rotated one and the standard layer, let's say it this way. We can put different layers on top of each other, either in ABBA fashion or ABAB fashion, if you always have alternating layers here. And this is kind of driven by the stacking probability. We'll write down this position, and then we can kind of stack with a certain height. You calculate the number of layers here, essentially stack a few layers on top of each other, which looks like that. So we'll come to this plot section. In before here we have the line of replacement, which replaces now the positions of the intercalating molecules here in the center with other dummy atoms. So we have the dummy atom HB now and the NO, which stands for nitrate. And so we have two different atom types or dummy atom types. To later replace them with water and nitrate. Everything else is already in its final state, essentially. The next step now is to sort the intercalation, because we have usually also ions within the galleries, and they will have repulsive forces interacting, and they don't want to be neighboring or too near to each other. So we add with the Monte Carlo part of discus repulsive potential here. So we switch chemistry between the two intercalation type atoms, and these dummy atoms are with a given energy scale, minimum distance between each other, and essentially the power of the radius and the potential. So the higher the exponent, the power in the energy term, the steeper the potential curve will decline. So this essentially gives you some kind of possibility to reorganize the different dummy atoms within the layers, and instantaneously afterwards we'll replace with a certain probability these nitrates with different, for example, nitrates, or the water positions with different water positions, because we have two different waters and three different nitrates. So if we do that, and we'll kind of omit all the oxide layers in between the intercalates, we are just left with the intercalating atom types. And you see it's now a wild mixture of atoms, and each atom, dummy atom, is now replaced in the following by another molecule. This is done usually in the domain menu, which is here. So you give essentially the domain list, and all the atoms, either termed I or N1, N2, and so on, will be replaced by the nitrogen structure, which is given here and essentially loaded here. This is done in a fuzzy way, so this is a straight exchange of the dummy atom with the molecule we have prepared in the very beginning of this macro. So if we have done that, kind of already a final structure is provided. So already the host gas complex will hopefully come up soon. So there are a few more parameters you can probably use. So you can do the orientation again and change the molecule insertion. However, that was done previously, and it's done in a separate file, which is a lot easier. Okay, now we have created the big layered system, and I don't know whether you can see it. We have different types of nitrate in here and oxygens. It's fairly hard to say because we have not marked them in different colors now, but you see that we have different orientations. For example, this nitrogen is differently aligned compared to this one and this one. And also, maybe at the edges, we might see that there are also oxygens in here on the top and the bottom, so they stand for water molecules. So this is essentially this macro. I just go through here. So I did some refinements here. Now we still have one metal ion here in the metal oxide layer, and now we have exchanged that. We have also given the particle a kind of a final shape. So we have now a mixture between aluminum and zinc. And yeah, that's done here. And what I've done in the very end, I've said when we replace now the zinc with an aluminum, then of course the ion radii change a little bit, and we can also change the distances of the environment of the new ion. So we're looking at the environment, the oxygen environment of such a central ion, and then we can move their positions a little bit. So we kind of put them closer to the new central ion or further away. This includes some strain into the structure and so on. And this is then our final structure, how you work with the domain menu and use essentially kind of a host guest void system. Okay, and then there is the third, the Boehmite macro. This reads like this. So in the beginning, it's very similar actually to the LAH macro. You read in the structure, then you, here a few atom positions are modified, a few parameters for the calculation. Then you have to create layers again, you have to stack the layers, then you have to cut your particle, and then you reach eventually the state which is plotted here in the JMOL window, the raw Boehmite. So this is essentially Boehmite. You see the layers are closer to each other, just hydrogen bonding in between the layers, so there's no space for intercalation. Then we have here very sharp cutting edges and artifacts, so lone standing hydrogens, or aluminum is terminating these oxygen based structures, which is of course not very realistic, so we have to change that. This is done in a kind of surface cleaning stage, again with the connectivity menu. So we kill or essentially delete all the lone standing atoms here, either aluminum, oxygen or hydrogen, with just nearly no neighbors. Then we replot it, and then we should see that all surfaces are terminated by oxygen now, which makes sense. So I've already cut the hydrogens from the top layer and the bottom layer because we need to now add other molecules onto the surface. So at first we really have to define the surface, and this is done of course in the surface menu. And here we cut on the top and on the bottom, and in a thickness of 1.6 angstrom we set now all surface atoms to surface atoms but with external property. So the external property can be used as the anchors of later added molecules to them. So I've exchanged here, for example, and highlighting all external atoms to sulfur, and at the edges we have replaced the sulfur to selenium atoms, and then there's the plot. So just look at this structure. So you can see that now the top phase and the bottom phase, the basal surfaces kind of are replaced with different atom types. So we have sulfur in the center, and here at the edges we do have selenium atoms. So these are different anchors and can now be used for adding molecules or atoms on top of them from the outside. This is usually done in the decoration menu. So here we do the decoration again on the cut top and bottom surface in normal mode. We provide a crystal structure or molecular structure, which we have already before employing this macro created, and we put it in this distance on top of the just created particle again. These molecules we put on top of it were previously created. They are octahedras. In the center we have tellurium, and surrounded it's a tellurium octahedron, again with oxygens. Here not oxygens in this case, so we have replaced the oxygens by argon for a different reason. So again, dummy atoms in use. So the idea behind it is essentially when we do a second decoration along these surfaces, again on top of oxygen atoms, then we don't want to put additional molecules here at the oxygen octahedra of these tellurium species. Okay, so we put the molecule on top of this structure. Then there's a block which assigns B values to those molecules, because the molecules can move more than the atoms in the layer themselves. So there's a molecular B value. That's just for the refinement, and a linear correlation factor that atoms which are far away from the bulk or interconnections have more possibilities to move. So this far away atom may receive a higher B value. So the next step is to surface functionalize these side phases, 1, 0, 1 phases essentially of Boehmite. So we essentially will do the same. We again set external atoms. Again, oxygens will be decorated, and this time in the multi-mode. So we have 3 anchor atoms, so we're looking for 3 oxygens on top of the surface, and then we put the tellurium on top of those 3 oxygens, mainly centered here. There will be a second bond to the surface, also to an oxygen atom, which will be a uranium atom, so atom 5, to align the octahedron a little bit. I'll show you that in a moment. So this is essentially the resulting particle, and when we look closely to the surface stabilizer, then we see that tellurium is essentially on top of 3 oxygen atoms here. It has 3 above and gives an octahedron, and this uranium atom is essentially only there for the tilt. So it's also a dummy atom and can pretty much tilt the octahedron a bit. Okay, with that, we have essentially functionalized both surfaces. Here again, the B values are assigned. What we have not done yet are taking care about the edges, so still the selenium atoms are here. We can now put another third line of decoration on top of the edges. Therefore, we have only the boundary local function here, so it essentially takes the center of mass of the particle, and from there it will kind of create the surface vector which aligns this decoration. Again, it's the same decoration of the tellurate. So if we plot that, we have now tilted here, if we zoom in here a little bit, octahedra on the edges of the selenium. And when we now clean up all our molecules on top of the surface to the correct atom types, so remove all the dummy atoms, exchange them to oxygens, we'll receive a a good looking nanoparticle and realistically surface functionalized one. So this is a bit difficult to see, but I just deleted all non-external atoms once, and here you see the cage of molecules on top of the surface, and you see which kinds of molecules I've prepared in advance to reach an octahedral coordination with the central particle. Alright, I think that's everything which is in here. So we are done with the macros. Okay, let's head back to the presentation. We've essentially seen now that we can create different models which have different properties like random effects in it or disorder. You may encounter integer parameters or size distributions in a sample. All these, let's say, issues will force you to calculate a structure more than just once. When randomization, for example, is considered, it might be possible that you have one parameter set, and from this one unique parameter set you can create different structures if you have such a random effect in your modeling procedure. That means you have multiple results because you have multiple structures, multiple scattering properties, and hence your data or your fit is different. It might be that you never can recreate a fit from a given parameter set. This is of course a problem. So one means to avoid that is to do the statistic and average over many particles of one parameter set. This is done with the ref and indiv value. So you need to just increase this value, then you do repetitive runs of one parameter set and then average the data in the end. The second problem you might encounter are integer parameters. Integer parameters, for example, the layer count in a stack structure, can be hardly refined in a linear way. That means when you increase the layer number, of course the size in the layer direction or in the stacking direction is a step function. So you add one more layer, then you just add like one additional nanometer in stacking direction, which cannot be linearly refined. And this might lead into local minima instead of global or the global minimum you like to find during a refinement. The third issue is, polydispersity, meaning that in real samples you most of the time have size distribution. Like here on the left, log norm distribution of particle sizes, and you need to model that in order to have produced the best fit to your data. This is also done with the higher ref and indiv, or a multiplication of repetitive runs in each generation. So how to do that you'll see in a minute. Firstly, I want to shortly introduce the way how to solve the problem with random functions. So in this code line, we, for example, replace oxygens by selenium atoms in a process of doping, for example, with a random function which is not even necessary, and times 10%. So in a probability range of 0 to 10%, the oxygens are replaced. However, we do not know where in the structure the oxygens are replaced. That is completely random. It might happen that just in a corner of your structure all oxygens are replaced, whereas in a second run of this line or of your parameter set you have an equidistant replacement of oxygens in your structure. So again, even this line forces you to increase the value of ref indiv and repeat your calculation and average the particles to make this probability value here meaningful. The second issue I mentioned are integer parameters, and one way to get around this problem is to manually calculate these integer parameters. For example, as I've mentioned, the number of layers. So in this kind of if statement here, when you run in one generation 100 kids, for example, then you can write that so the modulus of 20 kids, so each kid with number 20, 40, 60, 80, and 100 is then executed with this kind of parameter set. So you put in your, for example, size or your number of layers, and then this kit is all the time created with these parameters and is giving you the certainty that you have excluded this possibility of a bigger or smaller particle. And this is very important for an early search and modeling approach, not to end up in a local minimum. Then there is, of course, the implementation of polydispersity. So I'll just show you one way how to insert this kind of Gaussian function into your modeling approach. What I've done here is I've calculated the size in each of the repetitions. So I have 11 repetitions essentially here. So I calculate 11 particles along this Gaussian function. So this one is the first particle, this one is the last particle. So for the first particle, the size dependency in this function looks like this. So the particle size is the average size. It adds here ref indiv. So for the first particle, this value is 1. So this gives them minus 5 times 0.2. So minus 1 times 2.576 times sigma. So this is this value away from the average size in this Gaussian function. So refindiv counts up to 11 for all these different points, and then we have calculated different radii along this axis, so 11 different equidistant sized particles as an approximation. Then of course we have to consider that the weighing of all those data sets which result from this size function are scaled differently before they are averaged. So you have to calculate the scaling, so essentially the y-axis of this plot to each, or at the end of each of those particle calculation, structure calculation. And then you have kind of modeled this Gaussian function, and you can exploit it to a log norm distribution, whatever you want in every spacing you want to do that. However, I've approximated that with just 11 particle sizes. The more you'll calculate, of course, the more time and computational resources you need to spend on such a refinement. You'll find more details to this kind of ensemble approach and the paper which is mentioned here. Of course, again, you're scaling up the refinement, and then of course the computational costs scale with the same factor of repetitions, here in this case ref and indiv. Yeah, with that we probably can wrap it up here. So again, more information can be found at the listed sources. We do now have a new official Discus channel where you can ask questions, and you'll find help there when you need it. Again, there are regularly workshops which you can participate in. So thanks very much. See you in a bit.